Well, in a prior module in this series, we've described the power stage where we have added a transformer to get isolation between input and output, and recognizing that we also need an isolated path for the feedback signal that goes from output back to input. And so we've, much of that has been accomplished with the use of opto-couplers, but they do add some substantial amount of extra design and components and board area and even some electrical considerations that give us reason to want to try to figure a way to design them out and find another way to get isolated voltage without the use of an optocoupler. And a couple of those look like they have generated some interesting product solutions, which I'm going to try to describe to you. But first, let's just refresh our memory that the reason we're doing this is because the optocoupler does, in fact, take a fair amount of circuitry. If you look on the printed circuit board picture on the left, you can see that the power stage is in all of the upper components, but the circuitry enclosed with the red outline shows the optocoupler itself, plus the circuitry required to drive it appropriately. All of that circuitry is shown in schematic form over on the right, and again you can see that the optocoupler doesn't look like much. It's just got the light-emitting diode and then the optically sensed transistor in its own package. But all of the rest of the circuitry is necessary. We need a reference, and we get that in this case by using a shunt regulator circuit. We need some gain in that circuit, which this does have, but we need to make sure it's stable, so there's some compensating circuitry. We need to have a source of current for the optocoupler, so that has required a higher voltage source from somewhere over on the secondary side, and we've had to be able to regulate that voltage to keep from getting a stray feedback path through the optocoupler. So all of that circuitry is added stuff that we'd like to figure a way to minimize or eliminate. So what we're going to show is a couple of possibilities that have turned into useful products. This one is called an isobuck because it is essentially a buck circuit with an isolated output. If you look over at the schematic on the left, you'll see that this is a synchronous rectifier DC to DC converter circuit with an output inductor and capacitor, being the output filter, and it generates an output voltage which is regulated by the fact that there is a feedback path that goes back over to the input side and somehow gets into the circuitry that controls the switching of what's called here the high side switch and the low side switch, QHS and QLS. Now we know all about buck circuits now, and we know that we've also added this synchronous rectifier for a lot of good reasons, but in this case it allows us to do something a little bit extra innovative. We've got an inductor in the circuit, in the standard buck circuit on the left, but we know that a flyback circuit, as we've described earlier, is merely a coupled inductor. So if we put another winding on that inductor core, we would generate the circuit that's shown over on the right. And again, and we've got the same buck switching circuits, the power switch, the high side switch, and the synchronous rectifier. We've got the primary of the transformer is, in fact, the inductor that serves in the output filter along with the output capacitor, and we're still closing the feedback loop to generate the PWM signal to that switching pair of MOSFETs. But with the second inductor winding, and again with the polarity shown, we have the winding that we showed before in our flyback circuit. So that essentially is a transformer coupled flyback circuit on that secondary circuit which contains only a diode and an output capacitor, with the secondary of the transformer having the polarity shown by the dots. Now the reason that works is that, remember, a flyback transformer coupled circuit, the secondary conducts only when the primary circuit has been interrupted. So what happens with this circuit is that when the primary circuit would normally get inducted would be when would be interrupted, would be when the high side switch turned off and the low side switch turned on, which would drive the upper side, the dotted side of the primary of that transformer down to ground. And we have a regulated voltage on the capacitor at the other end of the primary winding. So that primary winding has a regulated output voltage, which is the output voltage which was defined by the buck portion of our circuit. But the fact that it is a regulated voltage on the primary, and now the current, though, from that is flowing over on the secondary, the coupling between the two says that we've got the same voltage with the turns ratio accommodation as needed on the secondary winding, and that regulates the output of our secondary winding without any ground connection. You see that when we have well, let me go to the next slide, which will describe this operation a little more thoroughly. This shows the current flow, again with two different versions, one with the high side switch on and one on the right with the high side switch off. And of course the synchronous rectifier is doing the opposite function. So you see the red line showing where the current is flowing. During the duty cycle portion of our buck circuit, when the high side switch is on and we're charging the inductor and the output capacitor, the current is flowing as the red arrow shows through the high side switch and through the primary of the transformer from top to bottom, and both to the output voltage, which is available on that output capacitor, as well as into the capacitor to recharge any charge depletion. And during that time, the diode D2, which is our rectifier on that secondary side, is not conducting because the polarity is wrong, and therefore the only current on the secondary is current coming out of the capacitor and to drive the load. And then when we change states and the high side switch turns off and the synchronous rectifier turns on, current that was stored in the inductor flows in the opposite direction now, and that is a decreasing current, but it is flowing out of the capacitor and down through the synchronous rectifier. And we could take charge out of the capacitor plus the energy that was stored in the inductance of the transformer, and during that time then the transformed winding of the secondary winding now provides current that flows out of the secondary winding and recharges the capacitor as well as delivers current to the output load. This circuit is made possible by the fact that we've got synchronous rectification, because now we can definitely get negative current through our buck inductor, and that negative current is what we transform over onto the secondary. But the voltage is regulated because we have regulated it according to our buck control loop, which is a non-isolated, primary side referenced, a ground referenced circuit. And what have I got to say? Here's some waveforms. Can you start again right from here?
Yeah.
And the waveforms for this operation is shown a little clearer on this slide, which shows, first of all, the high side switch and the synchronous rectifier switch alternating in their conduction period as the two waveforms at the top. The next waveform down is the primary winding, and you see the upper half of that winding looks like the current in a standard buck circuit, where it steps up and then ramps up according to the value of the inductance, except that when the high side switch turns off and the synchronous rectifier turns down, we can pull that current down to ground and below ground. And once we get below ground, we start to get induced current then because we forward bias the output rectifier on the flyback secondary winding. And so the secondary winding, you can see, has no current while the primary winding is peaking, and that's during the duty cycle portion of the period. And then in 1 minus the duty cycle, which is the off time of the main power switch, the primary winding current goes negative, and that allows secondary current to flow high enough to recharge the output capacitor as well as deliver current to the load. And it's regulated to a fair degree because it's being driven from the regulated voltage of the buck circuit over on the non-isolated side. So that's one approach, is to use what we call an isobuck topology that gives us an isolated flyback output from a non-isolated DC to DC buck regulator. But here is another look at a flyback circuit where we're going to try to get rid of the optocoupler in a different way. The circuit on the left is a conventional transformer-driven flyback DC to DC converter, isolated by the transformer action. This has got a single switch. We're driving with some pulse width modulation, the primary winding, storing energy in the transformer because it is really a coupled inductor because of the polarity shown and because we've made it that way. It has some inductance in it. And then when that switch is open, the secondary current flows, as we showed earlier, and we get output current that recharges the capacitor and delivers the output. And then traditionally, we have all this optocoupler circuit that measures the output voltage and comes back to control the pulse width modulation. What we want to do is be able to generate that information strictly on the primary side. And we can do that in a way that's not really very easy to do, but it is doable because we know that when current is flowing in the secondary of the flyback transformer, that is because there's only, that is the current that is the voltage that is transformed over to the primary winding during that portion of the cycle. Because of the turns ratio, the output voltage, which is defined by the fact that the output rectifier is conducting, we've got current flowing, and it regulated because we've already, let me just tell you it's regulated now, and I'll show you how in a minute. But it is regulated because during that portion of the cycle, we know what the primary voltage is. And let me show you that on the next slide. But what we want to do, you see, if we know that the secondary voltage here is regulated, we can measure it with the signal on the low side of the primary of the flyback transformer. So look at the waveforms to explain that a little better. We've shown the schematic again over on the right-hand side. But follow along with me on the waveforms. The top waveform is the power switch on the primary side, having an on period when it's high and an off period when it's low. And this, by the way, I might add, is with discontinuous conduction mode of operation. I should point that out because it is a requirement on this circuit that it is driven in a discontinuous mode, meaning that there is a time when we fully deplete the energy stored in the inductance of the transformer. So anyway, back to the on time of the power switch. During that time, current, which started from a 0 point, ramps up to some peak value. That current is causing a magnetic field in the transformer to expand, and we're storing energy in the transformer at that point in time and delivering nothing over on the secondary. If we look at the primary voltage, which is the fourth waveform down, it is just the input voltage that is across the primary, because we've got the on power switch on the low side of the primary going to ground, and the high side of the primary is connected to the input supply. So we turn the switch off at the end of the on time. The current that was in the primary transfers to the secondary, and you see that going from the second to the third waveform. And now that stored energy is going to be delivered to the output. And while that is happening, the voltage on the output, which was there because it was set that way because of the output capacitor, is across the winding on the secondary and is transformed over to the primary. So looking at the fourth waveform down, you can see that first of all, when the switching action takes place, there's usually a bunch of noise. You can see that ringing and all kinds of stuff there. And there's maximum current is flowing in secondary, but the voltage that's driven it is approximately the output voltage on the secondary side times the turns ratio of the transformer. Now, during the first portion of that waveform, that is as the current is being delivered to the secondary side, and we're going to deliver all the stored current because we're running this discontinuous mode. As that current diminishes, the implication of the impact of that current flowing in impedances anywhere in the circuitry, making it less than accurate, is diminishing because the current is diminishing. And as the current gets down close to zero, we still have the output voltage, but with almost no current flowing through the secondary. So we have the best and most accurate position of the output voltage transformed over to the secondary. So we're going to sample that voltage on the primary at that point in time, which is at just before the current reached zero on the primary, while there is still the induced voltage of the secondary side sitting over on the primary. That gives us a measure of what the output voltage is. We can compare that to a reference and decide what kind of a correction action it needs to be taken, and make the correction action in time for the next switching pulse, and change the pulse width to get more or less current depending upon whether we want to raise or lower that voltage. So that lets us get the regulation loop closed all on the primary side. So what we've talked about here are two innovative circuit designs which have allowed us to generate an isolated voltage from a different ground reference circuit. Call it the iso-buck and our non-opto flyback. Now, there are limitations to both of these circuit topologies, mainly the accuracy implications of not having the same kind of accurate feedback control that we've been talking about with an opto-coupler. So these applications are both intended for lower power circuits, but they also add a lot of design simplicity or reduce design complexity. So they fit in this plot at lower power levels, but at simpler and therefore lower cost implementations. And above some value, then you have to say that the optocoupler is still a viable solution. So we've talked about two approaches. One is the iso-buck, which uses a conventional buck, which has a ground referenced, a primary ground referenced regulated output voltage, and an isolated flyback voltage. And on the right-hand side, we've talked about a conventional transformer coupled flyback, but without an optocoupler because we're closing the feedback loop on the primary side by gating the sensing of that primary voltage to be at the time when it most positively represents the output voltage times the turns ratio. Now, there are a lot of applications for both of those devices. this is just several different suggestions. We could use either of those circuits, or we might want to have different grounds because of a noise issue, or just because for whatever the system requirements might want to have a different ground. So that's the upper left-hand corner where we could get multiple distinguished grounds for these circuits. We could get plus and minus outputs isolated from a different ground and use both of these circuits on the upper right-hand side. On the lower left-hand side, we're talking about referencing the isolated voltages to some other odd voltage that's not related to anything on the primary side, and that's doable because the ground can be referenced anywhere they want on that isolated output. And the fourth application is a benefit of only the isobuck, but it's in recognition of the fact that in addition to those isolated secondaries, we also do have a regulated, non-isolated output, which is our buck circuit over on the primary side, which could be used for primary side circuitry. So that just gives a variety of uses for this type of topology. So that ends this module, and we're going to go on now to show some practical design considerations for the products that have been designed to implement these circuits.